This section is on the derivative and rates of changes. So remember, we're going to be talking about tangents. A tangent to a curve, let's say y equals f of x. We want to find the slope of the tangent line at some point. To do this, we're going to consider a point nearby. We'll call it Q. So we have a point P, which is at a f of a. And we're going to have a point Q, which is near A, but not actually at A. And so what we will have is, you want to consider this point that's near it. And the slope, of course, between these 2 points is just the difference in the y's over the difference in the x's. So you've got f of x minus f of a over x minus a, and that's the slope between P and Q. If you visually look at this, let's say we have some curve here, this is your function. Here's your P and here's your Q. We're looking at the slope of this line. That's the secant line. And you've got this distance here between x and a. We're going to call that h, give it a slightly different name. And then we've got this distance here, which is f of x minus f of a. If we use the idea of h, then this is this point down here. This point down here is a. Since this distance is h, then this point is also could be thought of as x plus, or a plus h. So instead of calling it x and a, we can call it a and a plus h. So we can look at f of x as being f of a plus h minus f of a. It's just a different way to look at it. Don't get too freaked out about it. It's just a different way to think. The tangent line to the curve at that point is the line through P with the slope. Now, the whole idea is we're going to let this point Q get closer and closer and closer and closer to P until we actually get the tangent line. And the tangent line is the line that comes close to P, goes through P, follows the direction of the secant line, but actually only hits the curve at that one point. So this is your tangent line. And what you want to do is you want to find the slope, and it is just the limit of this secant line slope. So the slope of the tangent line is the secant line slope's limit. And the way we write that is the slope, it's equal to the limit as x goes towards a. So we're going to let x get closer and closer and closer to a of f of x minus f of a over x minus a. Remember, this is the slope of the secant line, and we're going to let a get closer and closer, or x get closer and closer to a. Provided the limit exists, it may not. If we use our a plus h notation, then we're actually going to let, if we're letting x go to a, we're letting h go to 0. We're letting this distance here become 0. And then we've got f of a plus h minus f of a all over h. So let's go ahead and do an example. Let's say we want to find the equation of the tangent line at y equals 2y equals x cubed at the point 1, 1. So first thing to remember is that the way you find the equation of a line is it's y minus y1 is equal to the slope times x minus x1. But we just said the slope is that limit. So the slope of this tangent line is the limit of this distance, of this difference quotient. y1 is 1, x1 is 1. So all we're going to do is first find that slope, because we don't know the slope yet. We know y1 and x1, but we don't know the slope. We're going to find that slope. It's the limit as h goes to 0 of f of, well, a is 1, because we're being at the point 1. So f of a plus h, or 1 plus h, minus f of a, which is 1, all over h. So we just need to go through and calculate this. Remember, function notation is really, this isn't, the x isn't important. So instead of thinking it as f of x equals x cubed, I like to think of it as f of x, f of something equals something cubed. So what I'm going to do is I'm going to think of it as I've got something cubed, then minus something cubed, all over h. And all I gotta do is put in what the somethings are. In the first something, it's 1 plus h. In the second something, it's 1. And now I just need to multiply this out. So I need to figure out what to do to multiply this out. To help with this, I'm going to actually let you know about something called Pascal's triangle. Pascal's triangle is we start with a 1, and then we do a 1 and a 1, and then we do 1, and 1 plus 1 is 2, and then we end with a 1. Then we start with a 1, 1 plus 2 is 3, 2 plus 1 is 3, and then end with a 1. So then this one will be 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then end with a 1. And then start the next row with a 1, and 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and end with a 1. And it keeps going like this. This pattern keeps going forever and ever and ever. And you're like, why are we doing this? Well, that's because it allows us to actually multiply out things like 1 plus h cubed. 1 plus h cubed will always multiply out as something times 1 cubed. Notice the 1 here and the 1 here. Plus something times 1 squared. We're going to reduce the power on the 1 by 1. We're going to add in an h. So h was to the 0, which that's why there's none there. Now h is to the first. Then we're going to add in something, and then we're going to reduce the power on the 1 to 1, increase the power on the h to 2. Notice 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 0 is 3. So each time those powers add up to 3. And then we're going to have something times reduce the 1 down again, which means it's gone, and we increase the h power, which means it goes to 3. Since we're doing cube, that's where you stop. Now what we have to do is fill in what those somethings are. And this is where Pascal's triangle comes into play. Pascal's triangle, you're going to cube it. So you're going to come down to the row that has a 3 here at the first spot. This tells me that my first spot has a coefficient of 1. Second one has a coefficient of 3. Second one has a coefficient of 3. Third one has a coefficient of 1. And then you can see that this will multiply out as 1 times 1 cubed is 1. 3 times 1 squared is 3 times h. 3 times 1 is 3 times h squared. And then 1 times h cubed is h cubed. So that's actually how 1 plus h cubed multiplies out. The reason I did that is we had a 1 plus h cubed here. So we now know how this multiplies out. You don't have to actually FOIL it out and write all the things out. You can just use Pascal's triangle every single time. Just another example, not that we're doing this one right now, but let's say I want to do something a little different than 1 there. Let's say I want to do x plus h to the 4th. Then we start with x to the 4th times h to the 0. There's something here, plus something, and then x cubed, and then h to the 1st, plus, again, that's going to be something, x squared. Notice I'm doing 4, 3, 2. H went 1, 2, so it's going to be squared, plus something. X is now going from 2 to 1. H is going to go to the 3rd because it goes 2, 3. And then plus something. X is going to be gone now because it's going to be x to the 0 and h to the 4th. Again, notice you're raising to the 4th power. You start with x to the 4th, you end with h to the 4th. Now you just need to figure out what those somethings are. So come back up here to Pascal's triangle, you come down to the row that has a 4 in the second spot. So it goes 1, 4, 6, 4, 1. So that means you will have 1, get a different color here just so you can see what's happening there. You have 1, 4, 6, 4, 1. Which means that's now multiplied out as x to the 4th plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th. And you can use this on any of these. So now let's go back to our problem. So back at our problem, we're trying to find this limit. So we're going to have my slope. Whoops, sorry about that. My slope now is the limit. I haven't done the limit yet, so don't lose it. I haven't done it yet. And I have 1 plus h cubed. So I have 1 plus 3h plus 3h squared plus h cubed minus h cubed. I'm sorry, not minus h cubed. Got to remember what I had. Minus 1 cubed, which of course is just 1, all over h. So remember, that's what we had. We had 1 plus h cubed minus 1 cubed. So this part here is the 1 plus h cubed, then minus the 1 cubed. Now just collect like terms. So we still have this limit because we haven't done it yet. Now collect like terms. We have 3h plus 3h squared plus h cubed. Notice the 1's canceled. Now notice that every single term in the numerator has an h in it. That will allow me to factor and cancel the h in the bottom. If you can't cancel this h in the bottom, you did something wrong. Go find out what it was. Don't just stop and say, I'm done, because you're not. So you should be able to pull an h out of your top and cancel the h in the bottom. If you can't, again, you did something wrong. Go find out what it was. So now that I notice, because I pulled that h out, my h's now can cancel. I can cancel that h with that h. And I end up with the limit, as h goes to 0, of 3 plus 3h plus h cubed. And this is now where we get to use our limit laws. The limit of a constant is just the constant. The limit of 3h means I just put 0 in for h. The limit of h cubed means I put 0 in for h. I'm sorry, that's an h squared. And I put 0 in for h. And then I see I get 3 plus 0, or 3. So I now know my slope is 3. So going back, I can now do this equation. Y minus y1 equals my slope, x minus x1. So I now have my tangent line is y minus, remember we were 0.11, so y1 is 1. 3 times x minus x1 was 1. So we get y minus 1 equals 3x minus 3, or y equals 3x minus 2. And there's the slope of that tangent line. All right. Another concept here is, let's do another example. Let's find the equation of this tangent line. Again, we're going to go through that same process. We're going to, again, use that point slope form. Y minus y1 is equal to the slope times x minus x1. In this case, I'm only giving you x1. I didn't give you what the y1 was, but I can find it quite easily. If you want to, you can think of it as this is f of x equals 2 over x squared. In which case, then you can actually think of this as y1 is f of x1, or f1, f of 1. So you get 2 over 1 squared, or 2. Now we got to find that slope. So let's go find the slope. So the slope, again, is the limit. The definition of the slope is the limit as h goes to 0 of f of x plus h minus f of x all over h. Oh, but we know what x is. So let's actually put in the x this time. The x again was 1. Not always going to be 1, but it's nice when it is. So it's 1. All right. So remember, we haven't done the limit yet, so don't lose this here. My function is 2 over x squared. So 2 over something squared minus 2 over something squared. Again, don't think of this as 2 over x squared. Think of it as something. You're going to fill in that something. In this first one, the something is 1 plus h. The second one, the something is 1. So all I'm doing when I do this difference quotient is I'm just rewriting what my function is equal to. And then I'm plugging in whatever's in the parentheses. All right, so now I got to figure out how to simplify this. So I've got 2 over 1 plus h quantity squared minus 2 over 1, which is just 2, all over h. Again, what I want to do, I can't just plug 0 in here because I tried to plug 0 in here. I get 2 minus 2, which is 0 over 0, and I can't deal with that because it's called an indeterminate form. So what I need to do is I need to simplify this in such a way so this h in the bottom can be canceled. Well, one thing I notice is I've got a fraction within a fraction, and I don't like fractions within fractions. Normally, you can do lots of different ways to simplify this. You can combine these into one fraction and then divide fractions. Or you can just say, let's multiply the top by the lowest common denominator at the top. The lowest common denominator at the top is going to be 1 plus h squared times the denominator of the other one, which is just 1. But if I do that to the top, I better do it to the bottom. All right. Now, when I do that, I'm going to go ahead and multiply out the top. I would not multiply out the bottom because the whole idea is to get rid of this h in the bottom. So if I multiplied it all through, I'd have to factor it back out. I don't want to do that. No sense doing more work than I have to. Remember, you're going to multiply this times both terms. So with 2 over 1 plus h squared times 1 plus h squared is just 2. And then 2 times 1 plus h squared is just 2 times 1 plus h squared. Again, don't multiply out the bottom. And you have that. I do need to multiply out the top. So I'm going to go ahead and multiply out the top. When I multiply out the top, this is going to be 2 times 1 plus 2h plus h squared. Again, I'm really using Pascal's triangle on that one. So I've got that happening. It is just 1 squared plus 1 times h plus h squared. And because it's squared, I have 1, 2, 1 when I look at Pascal's triangle. Go back and look at that. 1, 2, 1. All right, so. Okay, so now let's go back to here and figure out where we are. So now we need to simplify this, and I think we're going to go to a new page because I think we're getting a little long here on this page. So what we had here at the bottom is we had this limit. We're going to go ahead and multiply through and then collect like terms. So we have the limit as h goes to 0 of 2 minus, and what I had here was negative 2 times 2h plus h squared. So we're going to have minus 2 minus 4h minus 2h squared, when I take that negative 2 through, all over h times 1 plus h squared. Remember, that was your whole thing. That's everything we had. 2, and then the denominator. Don't lose the limit symbol because we haven't done it yet. So now when I collect like terms, I notice, oops, I lost something. I know that because I can't cancel. And I notice that I have this 2 here at the start. And then I have 2 minus 2. So I lost my 2 here. Oh, this shouldn't have an h on it. That's where my problem is. How, when you can't change pages, it always makes a mistake. Okay. All right, then 2 minus 2 goes away. So you have minus 4h plus 2h squared over h times 1 plus h squared. Now I notice the top can pull an h out. So we'll pull that out. Pulling out the h, I get minus, I realize you can take out more, but let's just take out the h because that's the important thing. Minus 4 plus 2h all over h times 1 plus h squared. And again, the reason I did this is because now I notice this h cancels that h. And what I've got now is the limit as h goes to 0 of negative 4 plus 2h in the top and 1 plus h squared in the bottom. Now I can use direct substitution. If I plug this 0 in here, I get negative 4 plus 2 times 0, which is negative 4 in the top, and 1 plus 0 is 1, and 1 squared is 1. So I now find my slope is negative 4. So if I hadn't been able to cancel this h, I couldn't use this direct substitution, but since I could cancel the h, I can use direct substitution and find my limit. So I now know my slope is -4. I have y minus y1 is equal to slope times x minus x1. Y was 2, y1 was 2, and my slope we just found to be -4, x1 was 1. So I get y minus 2 is equal to -4x plus 4. So y equals -4x plus 6. If you were to plot this function and this equation here at the same time, you would see that they are tangent. This equation is tangent to the curve at the point 1, 2. Tangents are very much related to velocity. Velocity is where if you have a position function, s equals f of t, that's your position function. And your total distance is how far an object travels over time. So the total distance is how far it travels over time. The displacement is how far the object is from its initial point. Again, displacement, if you go somewhere and you come back to where you started, your displacement is 0 because you're at your initial point. Your total distance traveled is a little different. When we talk about velocity, the average velocity is displacement over time. Again, displacement is just the distance f of a plus h minus f of a. Time would be over h. We have the same formula for average velocity that we had for the slope of the secant. And then we can talk about instantaneous velocity. How fast are you going at a very instant? And that velocity, which v of a for velocity at a point, is the limit as h goes to 0 of f of a plus h minus f of a all over h. So your slope of your tangent line and your instantaneous velocity are the same thing if you're talking about position function. If you want to talk about your speed, speed is different than velocity. Velocity has direction and magnitude. Speed is just magnitude. So you just take the magnitude of the speed, of the velocity, sorry. So as an example, suppose you have a coin, and that coin is going to drop from, let's say we drop it from the top of the Empire State Building. Or sorry, Statue of Liberty. The crown of the Statue of Liberty, which you can't go in anymore. But let's say you could, no, you can go into the crown, but you can't drop anything out of it because it's solid windows. Let's say you're inside the crown. That is actually 80 meters above the ground. And we want to know is what is the velocity after 3 seconds? So that's what we want to find out is what is its velocity after 3 seconds? So what we need is we need the position function of this object. So physics tells us that the position function, f of t, which remember position is s. So you can think of it as s. I don't like s because my s's look like 5s, but s is your position function at time t. Physics tells us, and we will derive this in this course, is -4.9 t squared. And the reason I'm using -4.9 is because we're looking at meters, so we're in the metric system. So 9.8 is the acceleration due to gravity in the metric system. And so we're using the metric system. And so we get that plus 80. Since we're dropping it, there's no initial velocity. So that's why it's this equation. Again, later in the semester, we will derive this formula for you to see where it came from. And we want to know the velocity at 3 seconds, so our A is 3. So the velocity at 3 seconds is the limit as h goes to 0 of f of a plus h, with a is 3. So f of 3 plus h minus f of 3 all over h. And so then we just need to multiply all that out and find out what it is. So let's use the function notation. So my function is -4.9 times something squared plus 80. That's my first function, minus -4.9 times something squared plus 80. That's my second function. So I've got my first, this function here, all over h. Don't lose that h. In my first function, this something is 3 plus h. In my second function, this something is 3. If you always do it this way, I think you'll find functional notation not so bad. Now we just need to multiply all this out and then collect like terms. So I got negative 4.9. I do need to multiply this out. It will be 3 squared plus 2 times 3, which is 6h plus h squared plus 80 minus 4.9 times 3 and I don't really care what 4.9 times 3 is. So we can just, or times 9 is, we can just leave it that way. But we have a minus, so it's going to be plus 4.9 times 9 minus 80 all over h. And then this will be the limit as h goes to 0 of negative 4.9 times 9 minus 6 times negative 4.9. And that is 9.8. No, it's not. Let's find out what that is. So we're going to have to calculate that. So I'm going to quickly calculate that. So 4.9 times 6 is 29.4. H plus h squared plus 80 minus 4.9 times 9 minus 80. That was a plus. Got that. All over h. And then you can go ahead and cancel what's like terms. So there's a 4.9 times 9, and a positive 1 and a negative 1, so those cancel. And there's a positive 80 and a minus 80, and those cancel. So what we have is we have the limit as h goes to 0 of negative 29.4 h plus h squared, and everything else canceled, all over h. Notice now both these terms have h's in them, which means I can factor, and then that h in the denominator can be canceled. So we'll go ahead and do that. That'll give me negative 29.4 plus h, and then we're going to take the limit of that. If I take the limit of a constant is just a constant, so it's 29.4. The limit of h will be 0. So I get negative 29.4 is my velocity at 3 seconds. The units on this, the top is displacement, which is in meters. The bottom is time, which is in seconds. So it'll be meters per second. And there is your velocity at that time, at time 3 seconds. It's negative because it's going down, which is good because you dropped it and it should be going down on the earth. If I want to find out how fast it's traveling, so I want to find its speed, then I'm looking for the velocity at when it hits the ground. Oh, we got to find out when it hits the ground. All right, so we're going to go do that and find out when it hits the ground. Okay. So we're going to go look at that value and when it hits the ground. And so we have to first find out when it hits the ground. So we need to know remember our position function was s of t equals negative 4.9 t squared plus 80. When it hits the ground, the position, actually that's f of t equals s. When it hits the ground, it's on the ground, so its position is 0. So we're looking at when 0 is equal to negative 4.9 t squared plus 80. So 4.9 t squared is equal to 80. So t squared is equal to 80 divided by 4.9. So the time is t is equal to the square root of 80 over 4.9. So we got to go find out what that is. So we'll quickly do the square root. So we're going to do 80 divided by 4.9. Then take the square root of that. And it looks about 4 seconds. So if we want to find out the how fast it's traveling when it hits the ground, then we'd have to go through the exact same process we just did to find out what the velocity would be at 4 seconds. And then you could find the absolute value of that to find out what time it is. I'm not going to go through the process. I think we can all see how to do the process, but it's basically the same idea. You just go through that. You would use the limit as h goes to 0 of f of 4 plus h minus f of 4 all over h. And then you find out what that velocity is. Now it won't be exactly at 4 because it's not exactly 4 seconds when it hits the ground, but it's pretty close. And then you go through the exact same process.